Hello, so continuing on Advent of Code, today we are going to do day 12. Again, so I'm going to skip all of the details and just give the gist of the problem. You can read it on your own time, but essentially what we have is we have a list of strings like this. So they are divided by a line, and each letter represents sort of an elevation, and we are sort of climbing. And for example, A is the lowest one, so 0, you can imagine it being. And then as you go in the alphabet, B is 1, C is 2, D is 3, until Z, which is the highest one, which is probably 26 or something like that, right? And we have S here, which represents the start position. And S, the value associated with it is A. So the elevation of S, we can uppercase S is considered 0 because, or you can name it 0, or you can start indexing from 0 or 1, whichever you want. But S represents, it has elevation A, right? And E is so S is the starting point, and E is the destination we want to go to, and E has elevation Z. So the highest elevation. So it's sort of, we are starting from position, we want to go to the top highest elevation, E here. We don't want to go to Z, we want to go to uppercase E, and uppercase E has elevation Z. And the rules of moving in this here is that we can move left, right, top, down, except there is one extra condition, which is the destination square. If I'm moving from one place to the other, the destination one needs to be one higher than elevation than the previous one, right? So that means you can go from, for example, B to C, but you can't go from B to E, for example. So here we start at the left corner, top left corner, and they just show us here a valid solution. And this solution, we start from the top, we go here, we go here, we go here, and then we go here. Basically, this means going down. This one means going down, and this one means going right. This one means going left. These arrows just means that, and this one means probably going up here. And so here we go down, and then we go left all the way, and then we go up. I think I messed it up a little bit. Maybe let me do it again. So we go down, left, down, left, down, left, and then we go up, then we go like this, we go like this, we go like this. Yeah, you get the, it's something like this, it's exactly like this. It doesn't really matter, but here we arrive at E. For this example, we arrive at E with 31 steps. The shortest path to get from start to E is going to take 31 steps. Each move counts as a step, right? So that's what the problem tells us to do. Now let's see how we can solve it. Okay, so I have here the day 12 input. And I have also just the example, so we can test first with the simple example and then move on from there. So the simple example is this one. So you can see already, first we need to get the input file. So we take our input file. Sorry about that. We want to open. Let's start with just the example first. We want to read it, and then we want to get each line separately, right? Because each line represents a row, so we can read and split by a new line. That will give us each new line. And so this, let's call it a list of rows. Except what we want to do, just so we can index properly with like a matrix with I and J, like this, let's just maybe call this grid, and let's just have this be a list of characters, and each row is just each line, right? And now what we need to do is we want to get, let's first define a couple of things that we need. So we know that we will need the elevation here, which we can just denote from A starting from 0, and then each next character increases by 1 elevation. And that's what we want here, so we can just start from 0. And in Python, to get all the, this is, by the way, here we have only lowercase letters, except S and E, which are uppercase, but they represent lowercase a and lowercase z, right? So what this would mean is here, we can just prepare an elevation, where basically with each letter, we will associate its index in a map, right? So that would mean, for example, A, 0, B, 1, C, 2, and we will go all the way to Z, which would be probably 25 or 26. 25 or 26, it doesn't matter. One of these two, depending on what index is, right? So to get all the lowercase letters, we just can use in Python, we can use ASCII lowercase like this. And of course, we want to import the string. And now with this elevation, we want, because in the grid, we will get just the letter. So we want to get the index from the letter. So we can just create a map that has as keys the values, the letters. So let's call this letter, and has as the index I. And so to get, we can just enumerate ASCII lowercase, right? Okay, so now with this, we have the elevation working properly. Now let's just quickly run it here, just make sure at each step we can have the right thing. So we do Python day 12. We didn't print it, so let's just print our elevation. Looks like we do have, it's maybe without a parentheses. Yes, okay, so now we have each with an elevation, and Z's elevation is 25, okay? Okay, so now that we have that elevation, we want to calculate the distance from a starting position. We want to calculate the min distance, right? So this would be min distance from start to E, right? Now the question is, how do we get start? Well, start is just the one that has the value uppercase S. S doesn't have to be on the top left corner. We could have had something like this with S here. That's totally possible. So we need to first look for the start position. And so to do that, what we can do, let's just make this say this is part 1. We can just go through the entire grid, right? So in range of our grid, let's just first say the number of rows is the length of the grid, and the number of columns is the length of the number of columns in each row, which we can just get with grid 0, right? So we go through the number of rows, and then we go through the columns, and then we check if this is the starting position, which means it's equal to S. Remember, S's elevation is A, so we can move, the problem says we can move only if the elevation of the destination is so only if the destination is basically minus the current is smaller or equal to 1, right? The difference is 1. And so when the value is S, S actually has elevation A. So let's just, once we get it, let's just replace it with A, because that's what we want to use for the sake of deciding whether to move left or right or not, right? I hope that makes sense. And so we do this first, and then we kick off calculating the distance using the positions I and J. Well, this is important because let's say we had something like this, right? Let's say we had X here. If we had X here, we cannot move right, but we can move down because S is A and A have the difference smaller or equal to 1, so we are good to go. But with the X1, we can't move. But if we leave it as S, we can't calculate the elevation difference. So we replace it with A because that's its real elevation once we find the position, right? Okay, so that's the idea there. And now we just need to write our min distance, and this is just classic BFS we can use, where with BFS, since we'll explore neighbors one by one each level, the first time we reach E, we are guaranteed that that's the smallest one because it's the first we were able to arrive to, and we are going level by level on the neighbors, right? So the first time we reach E, that's the smallest distance. Okay, so we need a queue for BFS, because BFS we want to take the one that we added first. We want to take it first, right? Because that's what allows us to get the shortest distance. And so we want to use DQ here. Okay, so we import collections, we import it. And what we want to start with, this start position, right? And so that would be, okay, I'm just going to change this a little bit and make it just I and J, so that it's easier to write. Okay, so we need to start with a list with just I and J in it, but we also want to keep track of the distance, because that's what we want to return at the end, the distance all the way to E. So, and initially we start at the start position, which no distance, so 0. Okay, so now we go through the queue, but we also, since we'll be traversing and we may visit a place multiple times, we don't, once we visit it and find the shortest distance, let's say from this position to E, if we arrive at this position from another place, that place took more time to arrive at C. Okay? And so we don't want to explore it. We already know the answer, and the answer we know is shorter. So we don't need to explore it. So we need a visited set to mark places that we visited. And of course, since at the start we start with I and J, that's we can add it because we are already visiting it. We added it to the queue. Anything we add to the queue, we can consider visited. Okay, so now we need to get pop from the start of our queue. So we pop left. Now, if you use pop left to remove from the front, you would have to add to the back with append. If you had used pop here to remove from the back, you would have to insert from the front, so that the first one you add is the first one you get, right? And so either the combination is either using pop left and append, or using pop and something like append left. I don't know if it exists, but adding from the start, right? Okay, so this is the one we are going with. And so this will give us the positions. Okay, let's call this SI and SJ just to mark as start positions, right? So we don't get confused. And we want to get the distance. Okay. And so here we want to visit neighbors, and in the problem it says that neighbors are, you can go left, right, top, or down, and so those are either going down with the next row, or going up with the previous row, or going left with the previous column, or going right with the next column. And we want to, of course, make sure we are still within the boundaries, because we are subtracting and adding here. We want to make sure we are still within the boundaries of the grid, so it's smaller than rows, and it's still not less than 0 as well. And similar thing for NG, and we want to check that it's smaller than columns. Okay, now what else do we need to do? We want to check if we have reached the end, right? Because the other thing is that, so here we have Z, we can move to E because E is represented by Z. But if we are coming bottom up, V to E, we can't move from V to E because the difference in elevation between V and the elevation of E, which is Z, is bigger than 1, so we can't move here, okay? And so we want to add E to the Q only if the elevation is correct. But we also, since we also want to mark to use the elevation of Z for E. So how do we do that? We can check if this neighbor is equal to E, right? That means here we want to check the elevation between Z, because E is represented by Z. So this would be the destination. And but the difference between that one and the one of the current one, which is I and J. So that's the elevation for grid at I and J. Let me just say this is like this. If it's smaller or equal to 1, that means we can move. So we are in a case like this. Or maybe it's or maybe it's, let's say, y, right? Let's say if we had y here, then we can move left to reach e, right? So if that's the case, this is valid, so we can add it to the queue because we can move there, right? So we can append. So this is grid. So we can append this, and I and j, and the distance increased by 1 because we did one move, right? And so d plus 1. Now what if it's not e? Then it's still, we need to check that the elevation of between the one we are going to, the destination, and the current one is still smaller or equal to 1. So where are we going? The destination is a grid for ni and j, and we need the difference between that and the elevation of where we are, which is I and j. Okay, so this is the destination and this is the current one. Now if the difference is smaller than 1, then we want to add to the queue. Now here we shouldn't forget to add to visited, right? Because e, we shouldn't, e, once we reach it we are good, but here we want to add to the visited, so that if we reach it again we don't repeat, right? So here add ni j, and I and j, right? And we want to now we want here to check if we reached e, right? So how do we do that? We can check if the grid at I, j is equal to e, right? That means we added it somewhere here, and we can just return the smallest one. Okay. Now you may ask, why didn't we do that check here, right? It should be doable, but it's just for the sake of BFS, usually it's done right after processing, so I just want to keep that pattern. And that should be it. So now let's just print this distance and make sure it's working properly. We don't need to break here because we know there is only one s in the input. Okay, so let's run this. Okay, looks like there is a problem with running this. Okay, so there is actually one problem, which is why it's running continuously here, is that we didn't check that ni and j is not visited, right? Once we visit, we no longer want to visit again, because then there would be a continuous loop, right? So here we want to check that this is not visited before we visit it. Okay. The other thing we want to check, because we may have reached E, but the elevation is not proper, so we shouldn't add that one. There is no use in adding it, right? Because then if we add it, we'll return D for that E, but that E is not working, right? So what we should do here is just make sure that this is different than E. Okay. Okay, so now let's run it and check if it's working. So we have 31, and that's exactly what we need here. So now let's just run it on the bigger input, which is day 12. And so if we do that, we get this value. So let's submit. It matches what we have here. Okay, so now for the second part, the only thing that changes is that instead of we wanting to just start from this S value, now we want to start from any elevation that has value A. So which means including S, because S has elevation value A. So for all of them, we want to start and get the distance to E. And from there, we want to get the smallest one. Right? We want to get the smallest one. So let's just write that. We already have a function that gives us the distance, so we can reuse it. So what that means here for part 2, we want to do the same thing here. Okay, and we want to check also if it's this, but this time we want to also check if it is A, because A should work. So this is also equal to A. Now, we still want to do this because in case it's S, we want to replace it with A. It's the same reasoning we said in part 1. And for those that are already A, nothing changes, so we can leave it as it is. And now we want to calculate the distance for this from this position. And if we get a value, which means it's not none because we weren't able to reach E, right? So if we are able to reach E, which means this would be a real value and not just none in Python, then we can just take the minimum distance with the results that we have so far. Now we need to initialize the result to a big value so that if we minimize with anything, we will get that value. But this will give us the minimum distance for for starting from any position that has elevation A, and when we reach E. So from any A to E, the minimum distance. That's for all A's in the grid, right? So that's what we'll get. And so here we'll just print the result, right? So let's run it again. And now we still want to run it on day 12 here. And we get a problem where because this needs to be without parentheses. Okay, so let's try again. And that gives us 375, the second answer. That's for part 2. The second printed value. So let's just check that. Okay, so the first one we got it. The second one, let me refresh. Yeah, that's the correct value, 375. Okay. Yeah, so that's pretty much it. Now, maybe I can just like clarify a couple of things here. So just to make this more readable, we can say, so this is something like this. So if it's E, so this is our destination, and this is the current one. So the current one. And what we want is destination minus current to be smaller. So if this is the case, we want to go like this. And a similar thing here. So once we determine it's not visited and it's not E, right? So this would be, of course, different. This would be the destination is the NINJ cell, and the current one is the one at cell IJ. Now, if destination minus current again is smaller, then we want to do this, okay? And yeah, the rest we can leave as it is. So I'm just clarifying this here. And that should be it. That shouldn't change the answer, so we can just rerun it again and it's still the same. Yeah, so that's pretty much it. We can use BFS and just apply exactly what the problem tell us to do. Yeah, so please like and subscribe, and see you on the next one. Bye.